Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with the 8th chapter of microwave engineering, where the microwave that has been generated we have seen in the initial chapters have been propagating, having a transmission through a guided medium, so which is a single conductor transmission line rectangular waveguide. We initially had the introduction to what exactly the parallel plate transmission line is, and then we shifted to such a metallic hollow tube. We have seen whether the propagation in the rectangular waveguide in the TEM mode is possible or not, and due to its unavailability we have gone through the analysis for the TEM mode, transverse magnetic, and the transverse electric mode. We have also solved selected problems based on to these modes of propagation. Now let us see the details with respect to the power transmission computed and the power losses that may occur while we have the microwave propagating through this rectangular waveguide. So here we start with our topic. The topic is power transmission and losses in the rectangular waveguide. So as we know that microwave is basically the electromagnetic wave with the specific frequency range of 1 gigahertz to 300 gigahertz. We have the power behavior in the microwave transmission, again governed by the Poynting's theorem. So the Poynting's theorem will give us the information in the complex form here. Now here we have a waveguide, and that has been terminated with such a load that there it is no reflection. So waveguide will have termination with no reflection. Also, the length of this waveguide is considered to be the infinite as compared to that of wavelength of the operative microwave inside it. Now with these assumptions we shall be making the use of the Poynting theorem to analyze the formulations corresponding to the power transmission and further the power losses here. So now the power transmitted through the waveguide can be simply denoted by capital P suffix TR as a suffix for transmitted power, and it is given by the closed integral for P dot of ds here. So P is also a vector form, ds bar is also a vector form. So this is nothing but by the next step we give it by the Poynting theorem as 1 by 2 in the bracket we have the cross product of E and H vector. This can be also shown in the complex representation with this ds vector here. So let us say this is the equation number 1 that is showing you the power transmitted. So here the direction of the power transfer that has been initially represented by the P vector is because of the cross product of E and H. We know that ideally the electric vector and that of the magnetic field intensity vector are mutually perpendicular to each other. So if we consider this to be the x direction, rectangular coordinate direction, magnetic to be in the y direction, the cross product results into the z direction here, the resultant into the z direction. This is for the Poynting's vector. So this is the information that we have from the Poynting theorem and represent the transmitted power. Now when we talk about the dielectric material to be of lossless type, so that time we can have the time average power. So the time average power flow through the rectangular waveguide can be expressed as P suffix TR again, and it will be 1 upon twice capital Z suffix G integral for the dimension small a for mod of capital E, which is squared over the dimension dA, the differential here. So by the next step, we can also express this time average transmitted power is equal to, in the form z suffix g divided by 2, where we have the integral over the dimension small a for mod of h square here, or mod is squared here, into the differential with respect to the dimension a here. Now here the mention of z suffix g in both of these equations, let us say the combined equation, it will be the equation number 2 here. So z suffix g inside the waveguide is nothing but the ratio of the magnitudes of electric and that of the magnetic component here. So it is Ex divided by Hy, and when you reverse the directions, so that time it will be the negation of the ratio of Ey to that of Hx here. We have represented in the equation number 2 this one and the previous in terms of mod of E square here. So mod of E square, or the mod square here, is represented as mod Ex squared added with mod Ey square in general, and similar is the case for mod H square is equal to mod Hx square added with the mod square of Hy here. So these are the two substitutions we can make into the previous two forms of equation number 2 here. Now we have the knowledge of transverse electric mode as well as the transverse magnetic mode. When we represent the transverse electric mode with the suffixes m and n representing the number of half cycles for the corresponding transmission here, the average power transmitted can be expressed as P suffix TR in terms of the parameters as like, we have the RHS computed square root of 1 minus Fc by F bracket squared divided by twice eta, and this is along with the integral multiplied to it for 0 to b, another one for 0 to a. We have inside the bracket Ex mod square added with Ey mod square with the differentials dx and dy here. So here the Ex Ey we have already explained that these are the corresponding resolved components in the x and y direction for electric field. These are the two dimensions, the broader dimension A, breadth it is, smaller dimension width, small b it is. So these are the two integrals over x and y components. Fc is the cutoff frequency, the minimum possible frequency while the mode of propagation is transverse electric. F is the frequency of microwave outside the guide before it has entered the microwave waveguide, and eta is the intrinsic impedance that can be given as square root of mu divided by epsilon here. Now further, when we consider the mode of propagation is Tm mode, suffix mn, it will be the same here. The transmitted power will be given by P suffix Tr is equal to 1 upon, we have twice eta square root of 1 minus Fc divided by F bracket squared, and now it is in multiplication to the double integral for 0 to b, 0 to a, over we have mod Ex square added with mod Ey square into dx dy here. So here the eta is the intrinsic impedance by the equation under root mu by epsilon, and this is in the unbound medium. So these were the two expressions we have represented corresponding to the TE mode and transverse magnetic TM mode for wave propagation inside the waveguide. So these were the power transmitted here. Now we shall be addressing the power losses here. Now the power losses are of two types. One corresponding to the dielectric material that has been filled in the cavity of the waveguide, and another corresponding to the walls of the waveguide. Ideally, we want the walls to be the perfect conductors, but practically it is not possible. So practically we select the highest possible conductivity material to manufacture the waveguide body there. So with the first type, we first of all analyze the power losses, that it is corresponding to the dielectric here. So the dielectric condition, we consider that sigma is very less than mu epsilon product here, where mu is permeability of the material medium in terms of Henry per meter. Epsilon is permittivity of the medium in terms of farads per meter. The product of the two is greater than sigma, which is the conductivity. So the conductivity we have here. So now the propagation, we know the propagation constant gamma is equal to attenuation constant alpha plus j times beta. So inside the dielectric having such a condition here, we obtained the propagation in terms of alpha is equal to sigma divided by 2 square root of mu divided by epsilon. In another form, we can express this alpha is equal to eta times sigma divided by 2 here. So this is the condition where we have the microwave in the unbound medium here. Let us have the microwave propagating into the bound medium corresponding to the transverse electric and transverse magnetic modes. So for the TE mode of wave propagation, T suffix Mn here, we have alpha suffix g that it is inside the waveguide here. It is equal to sigma into eta divided by twice square root of, we have 1 minus fc by f bracket squared. Whereas when we talk about Tm suffix Mn mode, so that time alpha suffix g is equal to sigma into eta divided by 2 in multiplication to the square root of 1 minus fc by f, the bracket is squared here. Now when we take the condition that the operative frequency of microwave before it enters the waveguide here is greater than that of the cutoff frequency here, so that time the attenuation constant alpha approaches for the waveguide condition to be equal to that of the unbound condition alpha, the earlier equation we have represented before the TE and TM modes here. So here if we reverse the condition, when we have f very less than that of the fc, so that time the alpha suffix g becomes very large, and as alpha is basically the attenuation constant, it results into the no propagation. So the power loss that we can say is of high extent, resulting into the no propagation condition when the operative frequency is selected like this, and this is with respect to the dielectric material which is filled inside the cavity of hollow metallic tube, that it is rectangular waveguide. Now we shall talk about the power losses because of the metallic walls that with the manufacturing of the waveguide is made there. So now by the guide walls to discuss, we go for the formulation of magnitudes of electric and magnetic vectors here. So the magnitude of electric vector is expressed as mod of, here we have E suffix 0z in multiplication to the exponential e to the power minus alpha suffix g squared here. whereas the magnitude of magnetic field intensity vector H is equal to mod of H suffix 0 z in multiplication to e to the power minus alpha suffix g, which is squared here. So here E suffix 0 z and H suffix 0 z are the field intensities at peak values. Selected the initial condition z is equal to 0 meters, I can say, as z is the measurement of distance, the direction of propagation of microwave inside the waveguide here. Now alpha g is as before the attenuation constant inside the waveguide here. Now further we shall be talking about the power loss. The power loss associated with can be given in terms of the time average power flow that decreases proportionally. So we have the equation of P suffix TR, and it can be measured in terms of P suffix TR plus P suffix loss with the effective multiplicand of exponential e to the power minus twice alpha suffix g squared here. So therefore we have for the P loss very less than P suffix TR, along with we have twice of alpha suffix g z very less than 1. So we obtain P suffix loss divided by P suffix TR added with 1 is equal to 1 plus twice of alpha suffix g into z here. And finally we obtain alpha suffix g is equal to the ratio of PL divided by PTR into the twice. So here PL is the power loss per unit length. So here we can say that the attenuation constant for the guide walls, hence the suffix g is mentioned, is equal to the ratio of power loss per unit length to that of the twice of the power transmitted through the waveguide there. Now we have the representation of the decay in terms of the exponential manner. So now instead of having the earlier equations representing the power loss, we can also make the use of a surface resistance denoted as Rs. So for the practical metal material having the highest or the higher conductivity, it will be giving us the surface resistance expressing how much the depth we can have the penetration into the walls of the waveguide due to the microwave propagation here. So this is basically related to the ratio of we have rho to that of the del. It is called as the skin depth. It can further be expressed as 1 upon sigma into del. So rho being the resistivity, the inverse is taken in terms of conductivity sigma here. Del is the skin depth here, and it can be further expressed as Rs square root of we have pi into F into mu divided by sigma, and it is measured in terms of ohms per unit square area here. So this is the surface resistance of the metal walls for the waveguide here. So by the use of this surface resistance, we can express the power loss per unit length given by capital P suffix L is equal to this Rs divided by 2 the surface integral over mod Ht square dot ds here. So this is in terms of watts per unit length here. Now here the representation of H suffix T. So H suffix T corresponds to the tangential component. Tangential component of magnetic field intensity capital H, which is a vector quantity, and this tangential to the metallic wall of the waveguide here. So if we have the substitution from these particular equations, we can result into the attenuation constant inside the waveguide alpha suffix g in terms of the surface resistance Rs, surface integral mod of ht squared into ds here as the numerator. So it is in place of the PL, power loss per unit length here, divided by here the denominator can be expressed as twice of z suffix g integral over the dimension a for mod of h squared into dA here. Now here we have mod of h squared is equal to mod of h z squared added with mod of h y squared, whereas we have mod of ht squared is equal to mod of htx squared added with mod of hty squared here. So the t is for the tangential case, and these are the corresponding rectangular coordinate directions under consideration. So this is with respect to the rectangular waveguide. We have the breadth into one rectangular coordinate axis, the width into the another rectangular coordinate axis, and the direction of propagation into the third direction. So here we have used the three parameters x, y and z here. So I hope these formulae that we have derived and discussed so far regarding the power transmission and the power losses into the rectangular waveguide will be helpful to solve the next problem based on to the power transmission and power losses in rectangular waveguide. For more such information regarding the concepts of microwave engineering topics and the practice of problems, you can subscribe to Ekeeda channel. Thank you.